All right. Today we're going to be doing problem number 1 of homework number 4. The problem specifically reads, show that if the variable x is greater than or equal to 0 and the mean of x, which is equal to theta, then the probability of x being greater than equal to the square root of theta is less than or equal to the square root of theta of eta. So what do we have here in this question? So we have our variable x, which we have these givens, greater than or equal to 0. All right, and that the expected mean is equal to eta. Okay, and we're asked to basically prove this right here. One of the clues that's given to us is that we're going to use this inequality, which is proven in the notes, the Chebyshov inequality. Hope that's pronounced correctly. Which basically says that the difference between any given x and eta, or the expected mean, if the absolute difference is greater than an error term, all right, that probability is going to be less than or equal to basically the variance over the square of that error term. So let's show how we can actually prove this. Specifically, we're going to be using a generalization of the inequality that's given in our clue. That is going to be called the Markov inequality, which we'll get to in a minute. This generalized form works in cases where f of x is equal to 0 for x is less than 0, which applies in our case here because of we're only working with x is greater than or equal to 0. And this generalization works when we have some variable which we'll call alpha greater than 0. Which here we will later on set equal to the square root of eta, which we'll get to in a minute. So basically we're going to be using the Markov inequality right here, which we'll derive real quickly. Basically, if we have our eta, which represents our expected mean, it's defined just like all of our expected means, which is basically the function times x, the integral from negative infinity to infinity. In our case, because we're working with only x is greater than 0, we don't have to go from negative infinity. We can go from 0 to infinity, in this case right here. Now, this term right here basically covers everything under the f of x curve, this integral, which makes sense that this term right here would be greater than equal to any other integral that works with an alpha, which starts at an alpha value greater than 0, which is how we actually defined it right here. Okay, so this integral, by definition, is going to be sort of like a subset of the area of this integral right here. Hence, this one will be greater than or equal to this. Okay? Furthermore, we can actually substitute our alpha value for x in here. And if we do that, basically what we're doing is saying, look, the very smallest value for x, which we'll use within this integration, okay, if we substitute it in and use it as a constant, it will always be, this term, this whole integral will always be smaller than that term. Why? Because as we proceed forward through the different x's, like alpha plus 1, alpha plus 2, alpha plus 3 to infinity, all right, if you actually broke this down, the alphas are going to increase and the x's are going to increase. So if we take the very smallest x, instead of multiplying each subsequent term by a bigger x, use this as a constant, this term right here is going to be smaller than that term right there. All right, so far we have this inequality right here, which we can further break down right here, okay, which is the definition of our probability function, which we break down right there. All we did in this case is take out the alpha value. And if this is our definition of probability, then what we're saying is that it's equal to alpha times the probability of x being greater than or equal to alpha. All right? So that's our equation right here. So what we've just proven is basically, and if we do some substitution, we can see how basically this probability, if we take this alpha and bring it all the way back over here, we can say that this probability here is going to be, because of these inequalities, less than or equal to eta divided by alpha, which we write right here, okay? So this is basically our terms right here. Now, if we substitute in, like I said, for alpha, and basically treat alpha, which can be anything, but we treat it as the square root of eta, this portion of the equation breaks down, which is eta divided by square root of eta is just eta. If we substitute in here for the alpha, again, square root of eta, we get this inequality right here, which is basically the square root of eta is greater than or equal to the probability of x being greater than or equal to the square root of eta, which is basically the term that we were trying to prove right up here. Hence, we have a provided proof of the truth of this term.